Generators offer a reliable power source during emergencies, ensuring essential systems remain operational. Generators can provide large amounts of power to support multiple emergency loads, such as lighting, pumps, and elevators. They can operate for extended periods of time, providing power until the emergency is resolved. Emergency battery units distribute power throughout the building, reducing the risk of a single event disrupting all emergency systems. Emergency battery units require minimal maintenance compared to generators. Emergency battery units take up less space than generators, making them suitable for smaller or more space-constrained buildings. Emergency battery units have lower operating costs than generators, eliminating the need for fuel and service contracts. New battery technologies offer long run times and extended lifespans, reducing the frequency of battery replacement. Given the advantages of both generators and emergency battery units, many buildings opt for hybrid emergency lighting systems that combine both technologies. This approach provides the reliability and capacity of generators with the decentralization and low maintenance costs of emergency battery units. The choice between generators, emergency battery units, or hybrid systems depends on factors such as building size and complexity, number and type of emergency loads, required level of redundancy, space constraints, and operating and maintenance costs. While generators have traditionally been the preferred choice for emergency lighting, advances in battery technology and the recognition of the risks associated with a single point of failure have made emergency battery units and hybrid systems viable alternatives. The best solution for a particular building will depend on its specific needs and circumstances. Firstly, let's discuss the reliable power source aspect of generators. In emergency situations, a consistent and dependable power supply is crucial for maintaining essential services. Generators excel in this area, offering a stable power source to keep vital systems running. Secondly, the large capacity of generators is a significant advantage. They can handle substantial power demands, supporting multiple emergency loads simultaneously. This includes lighting, pumps, elevators, and other critical equipment. Thirdly, generators offer long runtime capabilities. They can operate for extended durations, providing power until the emergency is resolved. This is especially important in situations where the main power source is unavailable for a prolonged period. Moving on to emergency battery units, firstly, their decentralized nature is a key benefit. By distributing power throughout the building, they reduce the risk of a single point of failure disrupting all emergency systems. This enhances overall system resilience. Secondly, emergency battery units require minimal maintenance compared to generators. This translates to reduced operational costs and less frequent servicing. Thirdly, their compact size makes them suitable for various building types, including smaller or space-constrained structures. They can be easily integrated into existing infrastructure without requiring significant modifications. Fourthly, emergency battery units offer a lower operating cost compared to generators. They eliminate the need for fuel and service contracts, resulting in substantial cost savings over time. Fifthly, advanced battery technology has significantly improved the performance of emergency battery units. New technologies offer longer runtimes and extended lifespans, reducing the frequency of battery replacements. Hybrid systems combine the strengths of both generators and emergency battery units. This approach provides the reliability and capacity of generators with the decentralization and low maintenance costs of emergency battery units. It offers a comprehensive solution that addresses a wide range of emergency scenarios. The choice between generators, emergency battery units, or hybrid systems depends on several factors. Firstly, building size and complexity play a crucial role. Larger and more complex buildings may benefit from the capacity and reliability of generators, while smaller buildings may find emergency battery units sufficient. Secondly, the number and type of emergency loads must be considered. Buildings with numerous critical systems may require the robust power supply of generators, while those with fewer essential loads may opt for emergency battery units. Thirdly, the required level of redundancy is an important factor. Buildings that demand a high level of redundancy may choose hybrid systems to ensure uninterrupted power supply in the event of a generator or battery unit failure. Fourthly, space constraints can influence the decision. Buildings with limited space may prefer emergency battery units due to their compact size. Fifthly, operating and maintenance costs should be factored in. Emergency battery units typically have lower operating and maintenance costs compared to generators, making them an attractive option for budget-conscious building owners. To delve a little deeper, let's talk about generator capacity planning. Ensuring that the generator selected is appropriately sized for the intended emergency loads is crucial. Overloading a generator can lead to failure, while an undersized generator may not be able to meet the demands of the emergency systems. Load calculation should include all essential equipment, such as lighting, fire pumps, and communication systems. Regular testing and maintenance of generators are essential to ensure their reliability. This includes checking fuel levels, lubricating moving parts, and inspecting electrical connections. Scheduled maintenance helps identify potential problems before they escalate into major failures. Fuel storage is another critical consideration for generators. Adequate fuel storage is necessary to ensure that the generator can operate for the required duration during an emergency. Fuel storage tanks should be properly sized and maintained to prevent leaks and contamination. Automatic transfer switches play a vital role in emergency power systems. These switches automatically transfer the building's electrical load from the utility power to the generator when a power outage occurs. Regular testing of automatic transfer switches is essential to ensure their proper functioning. Emergency lighting requirements are typically governed by local building codes and safety standards. These codes specify the minimum illumination levels, duration of emergency lighting, and placement of emergency lighting fixtures. Compliance with these codes is essential to ensure the safety of building occupants during emergencies. Battery unit selection should consider the specific lighting requirements of the building. Factors such as lumen output, battery runtime, and fixture type should be carefully evaluated. High-efficiency lighting fixtures can reduce the overall power demand and extend battery runtime. Battery maintenance is crucial for ensuring the reliability of emergency battery units. Regular inspection should be conducted to check for corrosion, leakage, and proper charging. Batteries should be replaced according to the manufacturer's recommendations to maintain optimal performance. Centralized battery systems offer advantages in terms of maintenance and monitoring. These systems consolidate batteries in a central location, making it easier to perform routine inspections and maintenance. Remote monitoring capabilities can provide real-time status updates and alert personnel to potential problems. Self-testing features are incorporated into many emergency battery units. These features automatically test the battery and lighting circuits on a regular basis, providing assurance that the system is functioning properly. Self-testing can reduce the need for manual testing and improve overall system reliability. Integrating emergency lighting systems with building management systems can provide enhanced control and monitoring capabilities. Building management systems can be used to monitor battery status, track maintenance schedules, and generate reports on system performance. This integration can improve overall system management and reduce operational costs. Considering the advancements in battery technology, lithium-ion batteries are increasingly being used in emergency lighting systems. Lithium-ion batteries offer several advantages over traditional lead-acid batteries, including higher energy density, longer lifespan, and faster charging times. These batteries can provide extended runtime and reduce the frequency of battery replacements. Solid-state lighting, such as light-emitting diodes or LEDs, is becoming increasingly prevalent in emergency lighting applications. LED offer high energy efficiency, long lifespan, and instant-on capabilities. They can significantly reduce the power demand of emergency lighting systems and improve overall system performance. Wireless emergency lighting systems are gaining popularity due to their ease of installation and flexibility. These systems use wireless technology to communicate between lighting fixtures and a central control unit. Wireless systems can be easily reconfigured to accommodate changes in building layout. Emergency lighting systems should be designed to withstand environmental factors such as temperature extremes, humidity, and vibration. Proper selection of lighting fixtures and battery units can ensure reliable operation in harsh environments. Surge protection is essential for protecting emergency lighting systems from voltage spikes and transients. Surge protection devices should be installed at the main electrical panel and at individual lighting fixtures to prevent damage from electrical surges. Regular inspections of emergency lighting systems should be conducted to identify and address potential problems. Inspections should include checking battery status, testing lighting fixtures, and verifying compliance with local building codes. Detailed records of inspections and maintenance activities should be maintained for future reference. Training of building personnel on the operation and maintenance of emergency lighting systems is essential. Training should cover topics such as system components, testing procedures, and troubleshooting techniques. Properly trained personnel can ensure the reliable operation of emergency lighting systems. Considering the integration of emergency lighting systems with fire alarm systems can provide enhanced safety and coordination. When a fire alarm is activated, the emergency lighting system can automatically illuminate exit routes and provide guidance for building occupants. This integration can improve the effectiveness of emergency response efforts. Smart emergency lighting systems use sensors and controls to optimize lighting levels and energy consumption. These systems can automatically adjust lighting levels based on occupancy and ambient light conditions. Smart emergency lighting systems can reduce energy costs and improve overall system efficiency. Energy efficiency is a key consideration in the design of emergency lighting systems. High-efficiency lighting fixtures, smart controls, and optimized lighting layouts can significantly reduce energy consumption. Energy-efficient emergency lighting systems can save money and reduce the environmental impact of buildings. Testing and commissioning are essential steps in the installation of emergency lighting systems. Thorough testing should be conducted to verify that all system components are functioning properly. Commissioning ensures that the system meets the specified performance requirements. Continuous monitoring of emergency lighting systems can provide real-time insights into system performance. Remote monitoring capabilities can alert personnel to potential problems and enable proactive maintenance. Continuous monitoring can improve system reliability and reduce downtime. Cybersecurity is an emerging concern for emergency lighting systems that are connected to building networks. Security measures should be implemented to protect these systems from cyber attacks. Cybersecurity protocols can prevent unauthorized access and ensure the integrity of emergency lighting systems. Compliance with industry standards, such as those developed by the National Fire Protection Association, or NFPA, and the International Electrotechnical Commission, or EIC, is essential for ensuring the safety and reliability of emergency lighting systems. Adherence to these standards provides assurance that the system meets the required performance criteria. Life cycle cost analysis is a valuable tool for evaluating the long-term costs of emergency lighting systems. This analysis considers factors such as initial investment, operating costs, maintenance costs, and replacement costs. Life cycle cost analysis can help building owners make informed decisions about the selection of emergency lighting systems. Resiliency is a key attribute of effective emergency lighting systems. These systems should be designed to withstand a variety of threats, including power outages, natural disasters, and human-caused events. Resilient emergency lighting systems can provide reliable illumination and guidance during challenging circumstances. Innovation in emergency lighting technology is constantly evolving. New materials, designs, and control systems are continually being developed. Keeping abreast of these innovations can help building owners select the most effective and efficient emergency lighting systems. Maintenance contracts can provide peace of mind and ensure the ongoing reliability of emergency lighting systems. These contracts typically cover routine inspections, testing, and maintenance activities. Maintenance contracts can help prevent unexpected failures and extend the lifespan of emergency lighting systems. Lastly, proper documentation of emergency lighting systems is essential for effective management and maintenance. Documentation should include system drawings, equipment specifications, testing reports, and maintenance records. Accurate documentation can facilitate troubleshooting and ensure compliance with regulatory requirements. Considering the financial aspect, incentives and rebates are often available for energy-efficient emergency lighting systems. These incentives can help offset the initial cost of upgrading to more efficient technologies. Contacting local utility companies and government agencies can provide information on available incentives and rebates. Building codes and regulations are subject to change. It is important to stay informed of the latest code requirements and ensure that emergency lighting systems comply with all applicable regulations. Consulting with qualified electrical engineers and code officials can help ensure compliance. Emergency lighting systems play a critical role in ensuring the safety of building occupants during emergencies. Careful planning, design, installation, and maintenance are essential for creating effective and reliable emergency lighting systems. Prioritizing safety and adhering to industry best practices can protect lives and property. The NEC, specifically Article 700, covers emergency systems. These systems are intended to supply power automatically to designated areas and equipment in the event of failure of the normal power supply. Article 700.12 provides details on the types of power sources that are permitted for emergency systems. These include storage batteries, generators, and uninterruptible power supplies. Article 700.16 specifies the illumination requirements for emergency lighting. It mandates that emergency lighting must provide adequate illumination to allow for safe egress from the building. Article 700.26 covers the testing and maintenance requirements for emergency systems. It requires that emergency systems be tested periodically to ensure their proper operation. For emergency systems relying on generators, NFPA 110 provides comprehensive standards for the installation, maintenance, and testing of emergency and standby power systems. NFPA 110 classifies emergency power supply systems based on their reliability and performance characteristics. These classifications are used to determine the required level of maintenance and testing. NFPA 110 outlines the requirements for generator sizing, fuel supply, and ventilation. It also specifies the requirements for automatic transfer switches and other critical components of emergency power systems. For emergency systems relying on batteries, NFPA 111 provides standards for the installation, maintenance, and testing of stored electrical energy emergency and standby power systems. NFPA 111 covers the requirements for battery selection, charging, and maintenance. It also specifies the requirements for battery monitoring and alarm systems. UL 924 is the standard for emergency lighting and power equipment. This standard covers the requirements for emergency lighting fixtures, battery units, and other equipment used in emergency lighting systems. UL 924 specifies the performance requirements for emergency lighting equipment, including illumination levels, runtime, and battery life. IEE 1584 provides guidance on performing arc flash hazard calculations. Arc flash is a dangerous electrical phenomenon that can occur when electrical equipment is energized. Arc flash hazard calculations are used to determine the potential severity of an arc flash event and to select appropriate personal protective equipment. Proper grounding is essential for ensuring the safety and reliability of emergency power systems. Grounding helps to minimize the risk of electrical shock and to protect equipment from damage due to electrical surges. The NEC specifies the requirements for grounding of electrical systems. Surge protection devices are used to protect electrical equipment from damage due to voltage spikes and transients. Surge protection devices should be installed at the main electrical panel and at individual equipment locations. The NEC specifies the requirements for surge protection of electrical systems. Load shedding is a technique used to reduce the power demand on an emergency power system. Load shedding involves selectively disconnecting non-essential loads during an emergency to ensure that critical loads can be supported. Load shedding can help to extend the runtime of an emergency power system. Remote monitoring and control systems can be used to monitor the status of emergency power systems and to control their operation remotely. These systems can provide real-time information on system performance and can be used to initiate load shedding or other emergency procedures. Emergency communication systems are essential for coordinating emergency response efforts. These systems can include two-way radios, public address systems, and emergency telephones. Emergency communications systems should be designed to operate during a power outage. Signage is important for identifying emergency equipment and exit routes. Signage should be clearly visible and should comply with applicable building codes. Emergency exit signs should be illuminated by the emergency lighting system. Considering the importance of regular training for building personnel on emergency procedures, training should cover topics such as evacuation procedures, fire safety, and first aid. Emergency drills should be conducted periodically to ensure that building occupants are familiar with emergency procedures. The Americans with Disabilities Act, or ADA, requires that emergency systems be accessible to people with disabilities. This includes providing accessible emergency exits, visual alarms, and audible alarms. Emergency power systems are often used to support critical infrastructure such as hospitals, data centers, and transportation systems. These systems must be designed to provide a high level of reliability and to minimize the risk of downtime. Sustainable design practices should be incorporated into the design of emergency power systems. This can include using energy-efficient equipment, reducing waste, and minimizing environmental impact. Building commissioning is a process of verifying that all building systems are functioning as designed. Commissioning should include testing of the emergency power system to ensure that it meets the specified performance requirements. Electrical safety audits should be conducted periodically to identify potential hazards and to ensure compliance with safety regulations. Electrical safety audits can help to prevent accidents and to protect workers from electrical hazards. Lastly, proper documentation is essential for the effective management of emergency power systems. Documentation should include system drawings, equipment specifications, testing reports, and maintenance records. Accurate documentation can facilitate troubleshooting and ensure compliance with regulatory requirements.